Good morning, everyone, and welcome to this lecture. In this lecture, what we are going to do is we are going to deal with the last part of this chapter, which is the force on a wire or magnetic force on a wire. This is what we are dealing with. Now, suppose you have a very small segment of a current carrying wire. If you remember, we call this small segment of the current carrying wire as a current carrying element. I hope you remember it. Yes or no? Current carrying element. Do we remember this current carrying element? Small segment of wire, current carrying element. This is a small current carrying element of length dl. As you can see, the current in the wire is I. It's a small segment of length dl, and it is placed in a magnetic field B, which is directed into the plane of the paper. Now, once this wire is placed, this current carrying wire is placed in this magnetic field. This current carrying wire contains a large number of charges which are moving. Because of this moving charges, you have current. A moving charge experiences magnetic force, and on similar lines, this small segment of the wire will also experience force. How much force that it experiences, the small force df that it experiences, you can see it here, the small force df that it experiences vectorly. If you write the vector equation, the small force that it experiences will be given by I into dl cross B. This is the small force that this wire experiences. This is the magnetic force exerted on a current carrying wire, a small segment of the current carrying wire, when it is placed in a magnetic field. This is the vector form of the equation. This vector form of the equation, this is the vector form of the equation which gives us both the magnitude of the field as well as the direction of this field. Force is a vector quantity, and therefore we have this vector equation, but we also have a scalar equation, and that scalar equation will give me the magnitude of the field. To write the scalar equation, I will write it like this: I dl b sine theta. I dl b sine theta. Well, can anyone tell me what is this theta? Can anyone tell me what is this theta? What will be this theta? What will be this theta? If you have magnetic field, if you have magnetic field in this direction and the current carrying element dl in this direction, both are vectors. Your magnetic field vector is going in this direction, and your current carrying vector dl is going in this direction. Then the angle between your dl vector and magnetic field is sine theta. So the scalar form of the equation has I dl b sine theta, This is the scalar form of the equation, which gives us only the magnitude of force. But how will I get the direction of force? To get the direction of force, I have to use right hand thumb rule. I have to find out the cross product of dl with b. I have to move my fingers again, the right hand fingers, dl cross b, and this will give me the direction of force. How am I going to move my fingers? dl is the first vector, so your thumb will point in the direction of dl or current. Your thumb will go in the direction of dl or current. Your palm will go in the direction of magnetic field. Palm will go in the direction of magnetic field. Then when you turn your fingers will point in the direction of force. dl cross b will give me the direction of force. Your fingers will point in the direction of force. Let us apply this on the diagram that we have drawn. My current is moving like this. My magnetic field is inside. This is dl. This is magnetic field. This is dl. This is magnetic field. If you turn your fingers are going like this, and that is the direction of magnetic force. Do we understand this? This is the direction of magnetic force on a small current carrying wire of length dl. Do we understand this? Please give me a thumbs up if you understand this. Okay, I'll give you 2 minutes to note this down. Let me know once you are done. Let's then move ahead. We have seen the direction and magnitude of magnetic force on a small segment of the wire. Question that is going to come in the exam will not be on a small segment of the wire. So let us now move on to the next heading. Magnetic force on a straight wire. What happens if your wire is not curved? In the first diagram that we draw, the wire was curved. If the wire is straight, then what happens? Magnetic force on a straight wire. If the wire is straight, let us say for example the wire is like this, carrying a current I. The length of the wire is L, and the magnetic field, let us say, is going inside. Now, how will I find the magnetic force on a straight wire? The actual formula is this only, I dl cross b. That is the actual formula, the vector formula. To find the total force, we will integrate this expression. Now, if you integrate this expression, remember magnetic field is uniform. It is not variable here. So magnetic field is uniform and the wire is straight wire. Magnetic field is uniform and straight wire. So what happens when you integrate this? All the forces will be going in the same direction. If you can see, I is upwards, magnetic field is inside. So all the forces, all these small forces df, all these small forces df on any segment of the wire will be going in the same direction. Do we understand what I am telling you? All these small forces will be going in the same direction. Do we understand this? So I can write the net force acting on the wire is I into the length vector cross B. I L cross B, because they are going in the same direction. So I can simply add them up by adding the lengths together, and that becomes your formula, the vector formula for finding out the force on a straight current carrying wire. Vector formula for finding out force on a straight current carrying formula, a straight current carrying wire. This is the vector formula. So there has to be a scalar formula. In scalar formula, F becomes I into L into B into sine theta. Where what is sine theta? Everyone can tell me. Everyone understands what is sine theta. What is sine theta? What is sine theta here? If your magnetic field is like this, B vector, and your current or your length vector is like this, angle theta is the angle between your B vector, magnetic field vector, and your L vector, your length vector. Do we understand this? Yes or no? No or yes? This will give you the magnitude. To get the direction, you will do the cross product of L with B. You will do the cross product of L with B. Right hand thumb rule. Your thumb will point in the direction of L, which is the direction of current. Your palm will go in the direction of field, and then you will curl your fingers, DL, B. You will curl your fingers. Your fingers will tell you the direction of magnetic force. In the case of the diagram that we have drawn, all these small forces or the total force is going in this direction. This is the direction of F. Do we understand this? I'll give you a minute to note this down. Let me know once you are done. Here also, you must remember two small points. If the angle theta is 0 or 180 degrees, that means your magnetic field B and your wire L are in the same direction, or magnetic field and wire are in the opposite direction. The force acting on this wire would be 0. Do we understand this? If angle is 0 or 180 degrees, the wire and the magnetic field is parallel, or in the opposite sense, force is 0. If I write the reverse, if theta is 90, force is maximum, and the maximum force is I L B. 90 means your magnetic field B could be like this, and your wire could be like this. Or your wire could be like this, and your magnetic field could be going inside the plane of the paper, or it might be coming outside the plane of the paper. Note this down as well. Let me know once you are done. Well, then let's move ahead, and I will give you a question to solve. Let me know once you get the answer. This is the question that I am talking about. A vertical wire carries current in the upward direction, is placed in a horizontal magnetic field directed towards north. What is the direction of force on the wire? I'll give you a minute. Think about this. So how are you going to solve this question? Let me try to explain it with a diagram that might make it more easy to understand. I'm making the diagram big enough so that you can see it. As you can see here, your current TL vector is in the upward direction. Upward direction. Magnetic field is towards north. So you can see how north is drawn. Everyone understands? North, south, east, west. We understand this? Current or DL vector is in the upward direction. North is this way. Current is in the upward direction. North is this way. And you can see your fingers are pointing towards west. And that is the direction of magnetic force. Your magnetic field was directed towards north. Do we understand this, everyone? How we have done this? Yes or no? Great. And this is the next question that is going to come. I'll give you 2 minutes to give me the answer for this one. 3 amperes current is flowing in a linear conductor, straight conductor, having a length of 40 centimeters. You have to be careful about the unit. The conductor is placed in a magnetic field of 500 Gauss. The main point of this question is Gauss. Remember, 1 Gauss, 1 G is 10 raised to the power of minus 4 Tesla, which is the SI unit. It's placed in a magnetic field of 500 Gauss at an angle of 30 degree with the direction of field. It experiences a force of how much magnitude only? I'll give you 2 minutes to give me the answer for this one. We got the answer, that is correct, option C. How are we supposed to solve this? It is pretty straightforward. Force is ILB sine theta. If I talk about the magnitude, I just need to put the values, get the answer, and stay happy. Force current is 3 amperes. Length is 40 centimeters, so 40 into 10 raised to the power of minus 2. Magnetic field is 500 Gauss, so 500 into 10 raised to the power of minus 4. Sine theta, sine 30 is half. If you multiply all these things, I think you are going to get the answer as C. And C, my dear friends, is the correct answer. Well done if you got this answer. Shall I move ahead? This is the next question. A conductor PQRSTU, each of side length L, is bent as shown in the figure. It carries a current I, is placed in a uniform magnetic field B, which is parallel to positive y-axis. Here y, x and z-axis are in a different orientation. What is the force experienced by the wire and its direction? I'll give you 2 minutes to give me the answer. So how are we supposed to do this, bacha? If I look at this pink wire, it is having current in this direction. Remember, the magnetic field is along y-axis. The current is along negative y-axis. What will be the force on this pink wire? Can anyone tell me? What will be the force on this pink wire? The angle between magnetic field and current or DL is 180 degrees. So force on this wire would be 0. Let me move on to this blue wire. This blue wire has current in the same direction as magnetic field. The angle between magnetic field and current or length element L is 0. So the force on this wire is also 0. Do we understand this? Yes or no? Yes or no? Great. Okay, now let me move on to this wire, the yellow wire. The yellow wire that the yellow wire is having current in the upward direction. And this ST wire will have current in the downward direction. QR wire and ST wire are having current in the opposite direction, so they will experience force in the opposite direction. So these two wires forces will cancel each other out. Do we understand this? Because they carry current in the opposite direction, so force will be in the opposite direction. Do we understand this? The only wire that is left is this SR wire, which carries current in the positive z axis. That is the only wire which will experience any force. The length of the wire is I. The current in the wire is I. The length of the wire is L, and the magnetic field is B. So the only answer that is matching is ILB. Current is in the outward direction. Magnetic field is in the y direction. So the force will go upwards along positive z axis. That is what it is given here. And that is the answer for this question, my dear friends. Do we understand this? Yes or no? No or yes? Well done. So this is the force on current carrying wire. Let us move on to the next question. And let us say I have in this question a rectangular loop carrying current I. The name of the loop is ABCD. The name of the loop is ABCD, and it is placed in a magnetic field which is going inside. Magnetic field is going inside. Now, can I ask you, what is the force on all these four wires? What is the magnitude? What is the direction? I must tell you the length of this rectangle is L and the breadth of this rectangle is, let us say, B. The length of this rectangle is L, the breadth of this rectangle is B. Can you tell me, bacha, what is the force acting on the four different wires? And then what is the total force acting on the loop? I'll give you 2 minutes to give me the answer. I hope you have tried this. Now, if I talk about this wire AB, which I can call as the pink wire, current is going like this, magnetic field is going inside, so the force on this wire will be in the upward direction. Force on this wire will be in the upward direction. If I call this force as FAB, the value of FAB, force on AB, will be I into L into B. The angle is 90 degrees and it is in the upward direction. I hope everyone understands this. If I talk about this green wire, BC wire, current is upwards, magnetic field is inside. The force on this green wire will be in this direction. Let me call it FBC. The value of FBC will be I into the length of this wire is B, magnetic field is B, and this force is going in the leftward direction. If I call this wire as the blue wire, current in this wire is like this. I is like this. Magnetic field is here, and you can see magnetic force will be going downwards. Magnetic force will be going downwards. Magnetic force on the wire CD. And if I write this magnetic force on the wire CD, it will be equal to ILB, but it will be in the downward direction. I hope you see it, everyone. Yes or no? If I talk about the fourth wire, the magnetic force on this wire will go like this, FDA, and the value of FDA will be equal to I into B, and it will be in this direction. If I find out the force on the entire loop, the force on the entire loop will be coming as 0. Do we understand this? Yes or no? Now we have done this exercise for a very simple loop, but this is applicable for any type of loop. What is applicable? So you write this as an important note. If any closed loop of any size or shape is placed in a uniform magnetic field, in any direction, is placed in a uniform magnetic field in any direction, the magnetic force acting on the loop will always be zero. No matter what is the size, no matter what is the shape, the magnetic force acting on the loop would be zero. Do we understand this? A loop of any size or shape, if I place it in a uniform magnetic field, the force acting on the loop would be zero. If my loop is like this, carrying current I like this, and the magnetic field is here like this, the force on this loop is zero. If my loop is like this, carrying current like this, magnetic field is like this, the force is zero. Any size, any shape, any direction magnetic field can be like this, then also it is zero. But the magnetic field should remain uniform. Do we understand this? This is a very important note that is going to solve a lot of very difficult problems in a very simple way. I hope that you can note this down. Let me know once you are done, because this is the last thing for this class. In the next class, we will wind up this chapter. Tomorrow with Saturday, we will be doing questions on this, and we will be winding up this chapter in the next class. So note this down and let me know once you are done. The class from my side is over. Take care and God bless you.